As you can imagine, casing and its different components can be very expensive, so choosing the correct equipment for the depth and pressure of the well is very important. It is usually up to the drilling team to calculate the least expensive casing that is capable of safely and adequately encasing the well so fluid can flow freely while containing the pressure that could lead to dangerous blowouts. Providing a margin of safety to protect the monetary investment, the crew, and the environment, casing designs can be critical, especially on deep, high-pressure wells. The well thickness and yield strengths of each string of pipe must be carefully planned to fit the conditions of the well. For example, if the casing pipe is too thin, the casing can fail, causing a blowout, but on the other hand, if the casing is too thick, then money is spent unnecessarily. Fortunately, there are computer programs that help simplify this process. To ensure adequate and safe design, there are 4 design criteria that the drilling engineer must factor into his equations for the casing design. The first is tension. Since all the casing hangs from the top joint, that joint must be strong enough to support all the strings. It is sometimes better to strengthen the upper part of the string by using a thicker wall or higher grade pipe. Of course, if a thicker wall is used, the engineer must account for this weight in his calculations for the rest of the strings. The next is the danger of collapse. This danger is greatest when cement has just been circulated up the outside of the casing, because the cement is much heavier than the mud that is inside it. The deeper the hole, the greater the outside-in pressure differential is. Strengthening for collapse is usually done at the bottom of the hole with a higher grade of casing. Third are burst stresses. Like collapse, these stresses are concentrated at the bottom of the hole. Critical time for burst stress is in pumping operations at the beginning of a cement job and during a fracture treatment or stimulation. The entire string is designed to be stronger at the top for tension and at the bottom for collapse and burst. The weaker casing pipe is usually in the middle of the string. The fourth is corrosion. In deep wells, higher grade pipe must be used to get the necessary strength because too thick-walled pipe can be too heavy for the tension. Higher grade pipe, however, is more susceptible to corrosion. For example, the presence of hydrogen sulfide gas is particularly troublesome because H2S can penetrate high-strength steel to become brittle and lead to cracks and breaks. In very deep, high-pressure sour gas wells, nickel alloy pipe is often the only solution. Because it is very expensive, it is used only when nothing else will do the job. Now let's turn our attention once again to the wellbore. In running casing and cement, the initial cementing, called primary cementing, creates a sheath or cover of hard cement that fills the annular space between the outside of casing and the wellbore wall. As I mentioned earlier, its primary function is to block fluid movement and pressure transmission up or down the annulus. Subsequent cementing is called squeeze cementing and is done to repair the primary cementing or in connection with a workover, a well that is being reworked because of declining production. Let me describe the various pieces of accessory equipment needed when running casing and then later cementing. In this illustration, you can view the typical equipment setup. At the bottom is a guide shoe. It has a rounded base that is run to the bottom of the casing string in the hole to prevent the casing from sticking on ledges. It can easily be drilled through later if necessary. Next is the float valve. It can sit either in a shoe called a float shoe or in a float collar located a joint or two above the shoe. The function of the float valve is to prevent mud from filling the pipe. It also provides buoyancy to the pipe, which then lessens the load on the derrick and the top joint of the pipe. As the casing is run in the hole, the casing pipe is periodically filled with water at the surface to reduce differential pressure that might cause the casing to collapse. Inside the float valve, the ball and seat type valve keeps the pipe closed while the casing is being run and opens it while the cement is being pumped in. The ball and seat valve also prevents backflow of either the fluid or the cement into the drill pipe. Next are the scratchers or wall cleaners. They remove mud cake from the sides of the hole. Attached to the outside of the pipe, these scratchers allow the pipe to make better contact with the sides of the hole as the cement is pumped into the annulus. As you might guess, smoother walls along the sides of the open hole allow a better seal to form between the cement and the formation rock. Radial type scratchers require that the pipe be reciprocated or moved in an up and down motion before and during cementing. Vertically mounted scratchers require the pipe to be rotated. Centralizers sit at the top of selected joints. They are attached to the outside of the casing pipe to center the pipe in the hole in preparation for cementing. Centralization of the pipe is essential because for maximum functionality, the cement sheath must evenly and completely surround the pipe. These are the essential pieces of equipment used in preparation for cementing. Let me now describe the process of running cement. First, dry cement is mixed with additives made up of accelerators, retarders, and density adjusters. The function of these additives is to adjust the dry cement properties to fit the conditions of the well. Accelerators speed up the setting time of the cement. Retarders do the opposite. They prevent premature setting in deep, high-temperature wells. Density adjusters increase the cement weight to reduce pumping pressures or to permit a higher cement column without fracturing the formation. After the casing is in place, the cement is properly blended with water and the hole is prepared for pumping. First, a hard rubber rupture plug is inserted into the casing, followed by the cement slurry. This plug will separate the existing mud from the new cement. Pumped to the bottom of the hole, the wet cement slurry, pushing the plug in front as it flows down, forces the rupture plug into the seat in the float collar. Once in place, the driller slightly increases the well pressure to break through this rupture plug. Once the plug is broken, the cement slurry displaces the existing mud in the annulus. When adequate cement has been pumped, a second plug, called a seal plug, is then inserted. This seal plug serves to separate the cement slurry from the fresh mud that follows. Finally, the cement slurry is displaced out of the casing into the annulus. The cement job is completed when the second plug, the seal plug, lands or seats in the grooves in the float valve. This landing is signaled at the surface by a sharp pressure increase. The pumps are then shut down, which allows the pressure to drop. The decreasing pressure causes the float valve to close, preventing the heavier cement in the annulus from running back into the casing. After the pumps are shut down, well operations are suspended for from 12 to 24 hours so that the cement can set. With the cemented casing in place, the next task is to perforate the casing in the zone of interest, now called the pay zone. Perforating means that the hole is lashed through the walls of the casing, the cement sheath, and continuing on for about 1 meter into the formation rock. It is through these holes that hydrocarbon fluids, will pass to the surface when production begins. To blast through the casing and cement, jet perforators are set to blast on average 4 to 8 jet holes per foot. Each shot is rotated 90 degrees or 180 degrees from the one above throughout the pay zone. To blast these jet perforators through the casing and out into the formation, casing guns are used. Both retrievable and reusable, these casing guns are made of strongly constructed steel which are run on an electric wireline. Before first firing the guns, the hole is filled with salt water. This salt water is called water blanket or load brine. When the well is perforated, the water rushes out through the new perforations, killing the well and preventing a blowout. With the potential for further damaging the formation near the wellbore, using overbalanced conditions, the engineering team may decide to stop further perforations until the well has been prepared for production. This means that the well will be outfitted with tubing, packers, and the Christmas tree to better accommodate perforating in preferred underbalanced conditions. In addition, many of the subsequent well treatment processes described in the next segment of this chapter are optimally done after the well has been outfitted with these three components. They include the wellhead and the various processes of preparing a well for production and will be discussed here. In preparing the well for production, smaller diameter pipe called tubing is installed down the casing with a packer at the bottom. Let me point out here that the permanent casing is rarely used as a conduit to get oil and gas to the surface. Remember, its main function, along with the annulus, is to seal the wellbore and keep it sealed. Instead, smaller tubing installed through the casing is used to bring the fluids to the surface. Manufactured in joints of 30 feet with threaded couplings, the diameter of the tubing can vary depending on the fluid amount projected to be produced. For example, small tubing that is 2 3/8 inches outside diameter is used for shallow, low productivity wells, while large 6-inch outside diameter tubing is used in high volume gas wells. In any case, tubing is smaller than either the drilling or casing pipe and is relatively lightweight when compared to them. Because of tubing's smaller size and weight, it can be run in and out of the hole by workover rigs outfitted with smaller hoisting equipment than you would find on a drilling rig. Here you can see that these strings hang from the tubing hanger in the wellhead and are retrievable, unlike the permanent casing strings. Keep in mind also that although only one set of casing is ever run, tubing, because of its smaller size, can be run through the casing in single, dual, or multiple strings. Inside the tubing, a packer is inserted and used to seal off the tubing from the casing. By sealing off the tubing from the casing, the more easily replaceable tubing protects the more permanent casing from the pressure and corrosive elements found in the crude oil or gas as they pass to the surface. In this illustration, for example, you can see a single tubing with a packer. In the second, dual strings can be seen side by side with a packer at the end of each string at different depths. A dual configuration is preferred when production from the well comes from two different zones that the engineering team wants to keep separate. In addition, dual or multiple strings offer economic incentives where warranted because only one well has to be drilled instead of multiple ones. Both dual and multiple strings can be installed, but multiple strings are less popular because of their mechanical complexities.